I'll say, good morning and welcome to CPRE 480, graphics processing and architecture. And I'm really glad you're here. Um, the first slide I typically show for a class like this is this one that has something of a very quick quote on it, where is a Buckminster Fuller quote, where there's no such thing as a failed experiment, only experiments with unexpected outcomes. And this is no longer an experimental class from Iowa State's catalog perspective. It's in the proper catalog, but it's very much an experimental class in terms of the assignments we will have in this class, what had to be updated from the previous time this class had been offered. And I want us to all come into this semester with that kind of spirit of this is all a big fun experiment. And I also want you to take the perspective that this is an elective class, and that to me that makes a very big difference in terms of what is acceptable, what I can expect out of you, and what I hope you to get out of a class that's at an elective level there. When it's a 200 or a 300 class, I feel somewhat of a large responsibility to make sure that that next generation of engineers has this sort of baseline training that you're not going to go uh, screw up too terribly badly when you graduate, and then you'll be set up to do great things. This is an elective class. We are all here, and it looks like 28 students are here today. We are all here because we want to learn more. We don't have to learn more. You're not required to take it. You're here because you want to learn more. And with that in mind, with the experimental nature of this class in mind, I want us to always keep that perspective. So we have different backgrounds. I could already tell that just from the introductions coming to this class. That's the other difference between a core and an elective class, the variance in backgrounds of students coming in. So very briefly, I just want to introduce what I mean when I talk about a course that's graphics processing and architecture. We'll start with what the term computer graphics even means, right? I think we know inherently what that means, right? It just aspects and all aspects of creating images using a computer. If you're creating images using a computer, you're dealing with computer graphics. So to start with, where did this image come from? This is my other car. My daily driver is a 2006 Honda Civic. But for the weekends and whatnot, when the weather's a little nicer, I take this one out for a spin. Well, what kind of car is this? It's well, first off, it's a render, right? It's an artist's rendition of a Lamborghini. How was it created? It was created using a piece of software that some of you may have used called Maya for modeling and rendering. And as we learn more about OpenGL this semester, well, Maya is an example application that's built on top of OpenGL. It doesn't have to use OpenGL for the actual rendering. And in fact, in this case, if you dig a little deeper, these type of renders with the somewhat overdone mirroring and lighting effects, those are almost always ray traced examples. So this is using a ray tracing renderer called Arnold. Underneath that, right? So that's the application. The application's goal is to render something. The software is a modeling and rendering software. Underneath that is the hardware, right? Some sort of PC workstation with presumably a graphics card for doing that modeling and rendering. When we talk about computer graphics, we can categorize it a couple of different ways. Maybe this is pretty obvious to a couple of you. Let's just start with the very basics here, and then we'll start to talk more about the details of this class in particular. We certainly can categorize it by what the specialty is. Oftentimes, when we're working just primarily in just two-dimensional images and restoring images or transforming images, that can be categorized separately as just something called imaging. There's modeling, so that task of figuring out what a three-dimensional object should look like and how the various components of it should interrelate. That's a traditional use case of specialty of computer graphics. When we refer to the word rendering, and it's a term I've already used here, that historically refers to building a two-dimensional image from a three-dimensional model. And we won't forget that part, but we're always starting with some three-dimensional view of what the world should be, what we're trying to see, and ultimately we're displaying it on a screen. At least that's the traditional historical definition of rendering, from 3D down to 2D. And we can add on top of that, once we start to animate things, the specialty of how do we simulate the changes in what we're rendering over time. That's what we refer to as animation here. We can also separately categorize computer graphics by the intention task. Certainly creating pictures or movies from your computer is a certain type of task. Computer graphics as part of simulating some physical phenomena is a very common use case as well. Somewhat directly related, but having a slightly different aspect of that is information visualization, using graphics to make something more easily understandable to a human viewer. That would be information visualization. And we can't forget video games. I think some people join an electrical and computer engineering department because they have a background or have an interest in video games. But it's not something to dismiss in terms of the size of that industry, in terms of the relevance of that industry, in terms of that industry pushing the future of computer graphics forward. It's not something we can easily dismiss. When we think about graphics on the entertainment side of things, it's just a couple relatively recent examples. I was thinking of what is a movie I've seen recently, what is a game I've played recently. So this is a picture of, for example, of a non-interactive entertainment, right? Your movie. So that's a relatively recent Pixar Disney movie called Soul. I like this example. I just found it online because it just shows that the importance of lighting. So this is a scene where there's the geometry of the subway scene in the movie, and that's without the lighting applied. When we add the lighting to that scene, and with the same exact geometry, it's the same exact frame there. There's a real significant difference in what that scene could look like. So as we talk about lighting this semester, we'll talk about a fairly traditional view of lighting and how we can apply it to a given scene. But really, lighting is everything. Geometry is important, but lighting is really everything. And in terms of interactive entertainment, there was a time when the difference between what we could do non-real time versus real time was significantly different. It's still different, but we're getting to a point where we're getting very close to what offline rendering can do with what we can do relatively fast in real time using all sorts of optimizations and tricks and taking advantage of the hardware that is available to us. That's the entertainment side. The engineering and scientific side is equally as relevant. This is a pretty well known high end model. I guess I would say this is the Boeing 777 model with the engine there. Um, it's a really cool model in a lot of ways. It's dated in some sense as well, but it's cool in the sense that a number of actual triangles that are in this model. That's one way we can measure model complexity. And in this case, it has over 350 million triangles in that model. Can't really tell just by looking at it, right? At that level of zoom. But it's basically modeling the entire CAD of an entire Boeing and Boeing plane down to all the electrical, mechanical parts associated with it. And being able to visualize that can be very helpful for all sorts of other design and optimization tasks. And then separately, you have scientific or engineering visualization. There, it's not always necessarily the number of triangles that is really impressive, but maybe the size of the meshes and the textures in the model. So, City of Helsinki, excuse me, has a model for their entire city, um, and something like 700 gigabytes of meshes and textures applied to that model to be able to render the entire thing. So it's a pretty impressive model in terms of the scale of it of being able to render something like that. So in terms of this course's, so that was the 10,000 foot view of computer graphics. We already got a question, Matt. I'm glad you're here today. We will. This class is focusing primarily on real time rendering. It's a class in which we can actually design the hardware for real time rendering. But my hope is we have a few weeks near the end of the semester. We're going to be talking about more physically based methods. That would be the right descriptor for it. How we can get closer to renders that look like that Pixar movie scene um, versus what one can do entirely in real time. But I think this slide is pretty important. So come back to me, those of you who have disconnected briefly. Um, this class's focus is on graphics processing. It's in the title, so that wasn't misleading. So it has to do with the software techniques and the hardware architectures for accelerating rendering and relating computational tasks. This is a class on graphics hardware. It is not a class on graphics software. We have to learn a lot about graphics software to be able to design graphics hardware. And similarly, this class assumes you have zero background in graphics software. If you have some, that's great. You can tell me when I make mistakes. You can push everyone a little bit further. That's great as well. But this is a class on graphics hardware. I think it's a wonderful topic to learn as an undergraduate student. It is a very fascinating problem domain. How do I get this type of render to work in a reasonable time, power, cost, budget on a chip? The algorithms, I think, are also interesting. Um, Extremely clever people have spent their careers developing algorithms to make certain effects be feasible and really realistic looking. it definitely, this third point here has very challenging implications for hardware, processor, and system design. And you'll be spending a lot of your semester, working through some of those challenges for processor and system design. And then this is relatively more recently, but the general programmability of graphics processing leads to applications for high performance computing that are something that you may find that even after you graduate, you may not go into computer graphics as an application domain as a field, but the use of graphics processing for just high performance computing is something that's very likely you'll be using, if not directly, certainly indirectly, after you graduate. Because that parallelism that's available to us in graphics processors is becoming increasingly important. And this evolution doesn't look like it's really stopping anytime soon. I think it's a fair statement to make that graphics processing is what is pushing computer architecture forward. So you've taken a computer architecture class before this one, and you've learned. I think the joke I used to make was you've learned 1993 computer architecture in that class, but you learned it really well. So you learned a lot in that class, and it's really been since then. Yes, there's been evolution of general purpose computer architecture, but in my opinion, it's really been on the custom computing side and then on the graphics processing side that has really moved that field forward since that time. So I think it's an important class for that reason. It's important to focus and relevant to focus on graphics processing in this course. There are other courses offered at these universities that are very good that will just teach graphics programming, and those are good courses as well. I have the same kind of caveat I have when I teach a computer architecture class as well. A pretty common question that I think is equally relevant for general purpose computing, but certainly for graphics processing, it's definitely the case. The perspective of a computer or an electrical engineer, where your perspective may be, I only want to learn about the hardware. I want to learn more hardware design in this class. I don't care about the algorithms. Can we just skip ahead and do the architecture? I certainly get that version of the question. I also get the other side of that question quite a bit as well. I'm a software engineer. I only want to focus on the software and the algorithms, and I don't care about the hardware. The truth is, those things are very closely coupled in the graphics processing domain. We really can't have intelligent discussions about hardware without understanding the underlying algorithms and applications. And vice versa, I believe, is also the case. Yes, you can use frameworks that try to abstract away some of the lower level details of your underlying graphics hardware, but it's definitely less the case for graphics processing than it is for general purpose computing that you can get by without knowing what your hardware is trying to do. The two, the architecture, the hardware and the software, you could say, directly co evolve. They directly co influence each other and they co evolve over time. Uh, and it's a chicken and egg type of thing, but they work simultaneously ultimately. Advances in graphics architecture lead to advances in graphics applications, algorithms, APIs, and vice versa as well. By having new application needs, new algorithmic ideas, new API changes, that influences how the architecture evolves as well. Where ultimately, sort of the shared goal between the hardware and software side of the building is to, what is the best 60 hertz, 120 hertz, maybe 240 hertz now image that you can generate for roughly $100 worth of silicon. And big picture here is that, yes, this is a class on computer architecture. This is a graphics processing class. You really need to get some level of familiarity with both sides of things. I'm not an algorithms person personally. I like algorithms. I know enough algorithms. Um, and the algorithms that we talk about here aren't ComSci 311 style algorithms. It's really more applied math when we talk about computer graphics algorithms here. It's something we should be able to handle. And it's a very common thing for a computer architect to have to know just enough algorithms to be able to figure out what does the implications are for our architecture. And that's how we'll be progressing this semester. We'll be learning a little bit of application, a little bit of API, a little bit of algorithms, and then discussing what the implications are for the underlying processor and system design as we go. This is the high level organization. I made a separate video on Canvas if you just want to check that out later. You don't have to be taking notes. That's perfectly fine. But this is my projected layout for the course. Going back to our initial quote of this being something of an experiment and there being no such thing as a failed experiment, it may surprise you to hear that I actually don't know how well this is all going to go. In terms of my projected layout here, when I teach 381, I have a feel, where the pain points are going to be, um, where I need to provide extra support, roughly what the average on a given exam or something like that is going to be. In a class like this, I have a plan. I have laid it all out on a week by week basis. I've done the work required to get that ready for you. How well it works in the end, I don't actually know. So we're going to find out as we go. But this is the plan, at least. We are going to have to be agile if necessary to modify the plan if the feedback is such that the current plan is not working well. So I don't like to think of this class as having lectures. I'm certainly talking a lot for someone who doesn't like to think of this course as having lectures. I call them learning modules. So we are in learning module 1 right now. The idea is it is overview of the main concepts we're covering, but I really do want to be splitting it up to have various in-class exercises, in-class technology demos as well. I don't want to be talking for 75 minutes twice a week. I could do that. You're all seniors or even some graduate students or on your way to becoming seniors. You don't need me to talk to you for several hours a week. These are going to be in this virtual environment. And then the other significant aspect of this class are the so-called machine problems. There's a historical reason we've called those machine problems. You can think of them as labs if the word machine problem sounds a little weird. The implication is there's significant hardware and software components. We're building a machine for each of those problems. Um, but those are our 5 labs we have this semester. These are going to be team-based assignments. They're graded based on completeness and effort. Um, and you could think of it as a combination of homework and lab work. You're building something as teams throughout this semester. There will not be separate textbook style homework assignments of that nature. And that's the majority portion of your overall grade in the class is how you do as a team on those machine problem assignments, with a few weeks left towards the end of the semester for a final project, which we'll talk about when we get closer to that point. That's just meant to be an extension of what you've already been working on in the labs to be able to show something that isn't me telling you what to do. You're proposing something that you'd like to continue to work on as a team and showing that off with the rest of the class. So you can see what's not here. I don't talk anything about exams. So for better or for worse, there are no exams in this class. I'm looking for expressions of people that they know this fact. Maybe they knew it already. I could have exams in this class. I don't think there's a need. I think you're really going to be able to prove yourself out through the effort you put on these machine problems to show, have you done well with this material? Have you put in a good faith effort in this class or not? I will also not have separate homework assignments like you would have had in your architecture course. The labs will have pre-labs, which have a bit of a homework flavor to them, but again, you're working on them with your team. It's not you sitting looking at the end of a textbook and trying to figure out the answers to questions for those. This is an applied, hands-on, experiential, and experimental class. We're building a graphics processor together this semester, and it's going to take some effort along the way, but that's really the goal. And it's not about did you study well enough for this particular exam here. A little bit more course logistics, so you can meet the staff. Most of you, but not all of you, know me. And for those of you who don't know me, stop by office hours at some point this semester. I'd love to meet you. Um, that's my office. I don't plan on being there, so you can meet me on Discord. There's our teaching assistant, Steve Brooks. He is here on Zoom. He wanted to also take part in the class this semester. He knows his stuff, and he's certainly been my right hand man helping me develop the lab materials this semester. That development is still ongoing, but we're ahead of where you are as a class, so we should be okay. Um, Communication is always key in a class like this. Some people have referred to this class as being like CPRE 381, but more of a grind. I don't think that's correct. I think how I would describe this class as being very real. There's nothing artificial about what you're doing in this class, and that's good, I think, for you. It's very real in terms of the lab experiments you will be doing, the assignments, the chip you'll be designing this semester. Um, but because it's really real, the labs have been designed such that that communication aspect is going to be critical. Communication with your team, communication with myself and Steve, the TA team here that we have, um, letting us know how things are going throughout is going to be really important. I want to know when things are hard. It doesn't mean I'll make them easier, but I want to know when things are hard and where the pain points are. Your pain points may not be the same as mine, and I do need to know that. So Canvas is kind of just going to be used as the class web page. It looks like most of you have already checked out Canvas. Um, Generally, it's going to be pretty static throughout the semester. The syllabus you could look through. It's got the 30 pages of boilerplate syllabus that's required now. The schedule, I use it as kind of a static calendar for what the plan for the semester is. So what you can do is, for example, click on week one, and you should be able to see, the PDF slides for what I'm talking about today. I'll post videos of what I'm recording here after this is over. Those of you who've taken 381 this past fall, it'll be in a very similar experience and Canvas interaction to that. Um, so that should work out pretty well. The actual lab postings will be there as well. And otherwise, there's some statically listed kind of resources for the various things we're doing this semester there. But otherwise, it's just like a class web page. So check that once a week. Grab the slides for that week. As a team, you'll want to be grabbing the lab assignment for a given lab that we have there. There'll be a video for that for most of those, as well as a link to the submission for that as your team. And that's basically all that I'm using Canvas for. Most of you have also checked out the Discord that we have for the class. Uh, Not everyone, but close enough to everyone. So I plan on being pretty active on there. Um, I think in the labs that we have for this class, the hardest part is knowing which question to ask. That if you can use your critical thinking skills to determine, okay, something is not working. Why is something not working? Oftentimes by the time you get that question well formulated, the answer tends to be not necessarily easy to solve, but have a clear path forward for how to address that question that you have. But I'll be pretty active on it. Steve, I expect, will be very active on it as well. And I kind of hope people help each other out as well. Um, this is not a Hogwarts style competition between groups that we have in the class. I want everyone to succeed. I think everyone can succeed. If you've figured something out, and you lost a few hours because of some silly bug in the software, and that will probably happen. Feel free to share that information. Right? Everyone should be able to succeed in this class, and helping each other out is one way we can all succeed. There's a brief question in the chat about class announcements. Yeah, we'll put them in both. By and large, I don't know how many announcements we'll see as we go. There's been a couple so far, but I'll be active every time there's an announcement. I'll post it in Canvas. You'll get an email if that's how you check things, and then I'll put it in Discord as well, and you can check it there. I expect our Discord to be pretty active. The one from last fall was quite active for CPRE 381. I expect this one to be fairly active as well. Um, we'll get there. We'll get there together. That's our staff for then this class, and I should mention, I guess it's important. Our final piece of the staff. There's our additional teaching assistants. So there's Joey, Tessa, and Johnny. They're somewhat anonymously there, so that to protect the anonymity of our grading that we have here. But they'll work tirelessly for you as well. Those of you who come to the occasional 2 a.m. office hours, you may see a kid with me as well. Textbook wise, these are all recommended but not required textbook. I'll take just a minute to discuss these. I talked about them in a bit more detail in the sort of syllabus video that you view offline if you're interested. Um, these are 3 different resources that I have found helpful in my own personal understanding of this topic. The first one is I'll call it the Angel book, the Edward Angel book, interactive graphics, a top-down approach. Um, this is a pretty good intro to computer graphics style book. Um, if I had to assign a textbook, if I was required by the university to assign a textbook, I probably would have assigned that one. It's gotten a little dated, not just because of the year 2011. There's been a lot of evolution in computer graphics, algorithms, and architecture since then, and he's not been so interested in trying to update his materials. Even he has a more recent version of that book that is also, I would say, equally out of date. But it's a good starting point in terms of I discuss something in class. If you see a slide, you can always ask me a question, but a lot of that is coming from what he is originally proposing and talking about in that book. So it's a good book. It's just a little bit dated. That's why I certainly didn't want to make it required. Real-time rendering is an outstanding book. It should be on your bookshelf if you're going into this field, certainly after you graduate. The reason I didn't make that a required book, it's a bit much. It's a bit probably too advanced. I think if everyone here took this class and then we had a 580 class happening afterwards, that would probably be a good required textbook for that class. So after you take this class, having that on your bookshelf would be a good thing to have. It's definitely not dated. It's definitely kept up to date fairly frequently. It's a lot. There's a lot of really good deep stuff in that book. And then finally, there's sort of the OpenGL programming guide. We will be doing a decent amount of OpenGL programming. It's a good resource. It's not required because it's all equally available online. So there's really no reason to force you to purchase it. I don't have you read through it. Oftentimes, the Google and find results method works pretty well for OpenGL. You just have to make sure you're looking at the right version of OpenGL. We'll talk about that a little bit as we start to get into that topic next week and the week after. Um, there's been a pretty big sea change in terms of how we do OpenGL, and so you do have to be careful. Are you using a version of OpenGL that is potentially either too new for us to be able to support in our labs, or too old for us to be able to support in our labs? We have to hit that right spot. So all three of these books are good. These are three good books for us, but none of them are required. They're all available either at the library. There's one that I posted on Canvas. Um, and one is basically freely available online. But none of them will be required reading. It'll just be influencing what we're doing this semester. Here's our tentative weekly layout of how our week is going to go. It's interesting because we just have the one lab section. So I think basically everyone is on the call here today. So we have our lectures on Tuesday and Thursdays. My office hours will be immediately afterwards, just in Discord. So come join me in office hours, and happy to chat. Um, our lab is in at that time on Wednesdays, 9:30 to something or other. It's a 3-hour lab on Wednesdays. Um, I don't recall the exact time. It's possible I have this slightly wrong. Anyway, it's Wednesday morning for our lab time as well, and we're all going to be in that lab together. So we do have lab this week. I have to get teams assigned first before we get started on the lab. I don't think you can even see the assignment in Canvas until you're assigned to a team. Thank you, Steve, for the update there. It is kind of a weird time, so bring a lunch for our virtual lab sessions that we have. The teams are pretty vital for, I think, your success this semester. So I want us to be careful with how we pick teams, and not just whoever you happen to know as your teammate for these labs here. And we're going to get started this week. Talk a little bit more briefly about what I mean by these machine problems. We have a semester long goal, and the labs will be building upon each other in a reasonable way this semester as we go. And our goal is the design and implementation of a graphics processor. And I've called it the simple graphics processor. The design goal of that is to be an OpenGL compliant GPU that we're building. That is a pretty big task. You will see some other hardware courses that cover computer graphics to some extent, where they build a little custom VGA core that can render a triangle. That's a relatively simple thing. Ours is interacting with OpenGL software that you will be writing, that will be both running on a workstation that you're connecting to, as well as then hopefully running on the board that you're also physically connected to. We're going to start with very simple fragment processing in the first couple of labs here, and we're going to be adding features on a week by week basis. At the end of the semester, we should be able to be running real things on that. Performance is always a little hard to predict, and our goal isn't to necessarily get the fastest performing anything. This is a teaching opportunity this semester. It's not we're not building a product that's trying to be competitive on the market, but we should be able to run basically all sorts of OpenGL applications written within certain restrictions, and run that on the hardware that you were designing with your team this semester. So this is a hardware design class. If you're here today and you're saying, I haven't done any hardware design, it's not a requirement. It is important that you be on a team in which you have team members who have done hardware design along the way. And I mean CPRE 381 style hardware design, or EE 330 style hardware design. If you've done that and you have enough of that expertise on your team, there's enough work for everybody. You're all going to get to learn together. but this is an FPGA based design class using a particular FPGA board that we've purchased for this purpose and the Vivado 2020.1 software for you to do that design. Um, we'll also be using it for simulation as well. It's very similar from a simulation perspective to what many of you would have experience with Model Sim, but that is just one small piece of the puzzle this semester. When I mentioned this is a very real experience, a very real course, you're going to feel that very acutely when you're working on these labs. That getting something to work in simulation is an important step. Maybe it's 10% of the way there, and you have to get the additional 90% of the way there for each of these machine problems as we go. And because we're trying to be compliant with real standard OpenGL, there is a pretty big software stack we have developed as well, where we've already written our custom OpenGL library, basically a driver to support that hardware platform that we're using. And on a week-to-week basis, you can think of these assignments as having three significant parts. There's going to be a software part. There's going to be someone who's going to be responsible for understanding the OpenGL that is relevant to that week, that MP's assignment. There's going to be a driver part. How do I get from the OpenGL calls to ones and zeros over a wire? A lot of that will be provided for you, but you'll have to kind of extend upon that on a weekly basis. And then the hardware aspect of things, understanding the algorithms down to the hardware. What does it mean to do a rasterization of a triangle in hardware? How do we design that? How do we model it? How do we code it in VHDL or Verilog? How do we simulate it? How do we actually get it to work correctly on the board? It's not a rough division between those various tasks here. It's probably more heavily weighted towards the hardware design aspects than the software side, but there's significant aspects of both on a week to week basis here. It's going to be fun. At least I'm looking forward to it. My goal isn't to scare you off, but I see some fear in your eyes. That's okay. You'll be able to figure it out. And the first one's really a platform introduction lab. That's our MP0 here. I'll talk about that in just a moment. Our MP0, where we don't have the whole graphics processing set up yet. Our first week in lab, really tomorrow as we get started. My goal is primarily to make sure the teams exist. The teams figure out a work plan that is reasonable. We'll have to be a little careful with how we balance our hardware and software resources that we have in terms of the lab infrastructure and really just to read through and get started. That's my goal for tomorrow. So to begin with, we don't have the simple graphics processor yet, and we're building a separate sort of one-off assignment, and that's to design and implement a processor to perform matrix vector multiplication for matrices and vectors of size 4. That's a very relevant assignment in a lot of ways. That particular operation of a 4 by 4 matrix multiplied by a 4 by 1 vector is extremely common, well, in all sorts of fields, but it's extremely common in computer graphics. We won't be necessarily building that and using that in our GPU. There's different ways we can support that in our programmable GPUs, but that particular operation and making that operation as effective and efficient as possible is a very relevant task in computer graphics. So it's a bit of a one-off. It is really, getting the teams functioning, making sure everyone can just access the technology. There's a lot of technology going on this semester. Making sure we have gotten started and the team, your roles and you know how you're going to work as a team. It's not senior design, but it has some elements of that. There's clear tasks that have to be delegated. Teams have to come together at periodic intervals to make sure that progress is shared and that everyone understands what the final goals are. There's a decent amount of teamwork in this class. So I'll be providing, as with most labs, a lot of the starting place for you. I won't be saying, here's nothing, get going. I'll give you something that kind of sort of works, and then your job as a team is to see how do we improve upon this? How do we add to it? How do we make this work in practice? But this first assignment is also a pretty good example of my personal philosophy, which is I'm not going to tell you how to do it. I'm going to tell you what I want you to do, and that's up to your team how you're going to do it. So there's a question: should we use VHDL or Verilog? Uh, the TA and I probably disagree as to what our preferred answer for that would be, but either's fine. My assumption, I created VHDL top levels for everything, so that's my assumption is that's how you'll be editing things. But it doesn't actually matter. The tools will work just fine with either. You just have to make sure they kind of play nicely together. If I have to pick one, I would say use VHDL for this. It's what we did in CPRE 381 that many of you took. It's what you should probably be most comfortable with coming into this class. But I'm not going to tell you that. And I'm not going to say, use this particular strategy to implement this matrix vector multiplication in VHDL. I'm going to tell you what a correct result looks like, that you know you're done and you can stop once this is the case. And the implementation strategies, it's really going to be up to your team. Always happy to answer questions. Always happy to help, debug things when something is going wrong. Walk you through ideas. Do a review of a design before you get started. Very happy to do all those things. But I'm never this semester going to tell you that you must do something this particular way within certain, restrictions as we go. So the teaming is, I would say, exceptionally important this semester. So I think our first in-class exercise looks like some people have already done this, and that's fine. Is to go through our project team formation. So I think it's pretty important we do this. I'm not telling you to pick your teams. I'm asking you to fill out a survey. So what we're going to do is go to Canvas. If you haven't gone there already, I'm going to open up the schedule page here. And in that first week, everyone should have access to this team formation survey. And actually, so what I'm going to do once we get started with this is I'll probably just stop the recording at this point, but we can stay here and make sure everyone has filled this out. I want everyone to fill this out today. It's going to ask you questions such as just answer honestly. What is your VHDL experience to this point in the semester? To this point in your academic career? If the answer is one, I guess, or zero, just put it. That's fine. Likewise, your C programming background, just give an honest assessment. It's fine. Likewise, with graphics background, if you don't have any, that's also perfectly fine. Now, I would add if you have no VHDL, no hardware design background, and you have no C programming background, and you have no graphics background, it's going to be a tough class for you, I would guess. But you'll be as part of a team, and the team will have different roles, and you can have different specializations within that team, as long as you're all able to work hard towards a common goal. There is not a typo, but sort of a changed reality on this slide where I say teams will be of size 2 to 3 inclusive. That is actually incorrect. There's been some changes since I put that together. Teams will be of size 4. So there are, as of today, 32 students registered in the class. 31 people here today, which isn't bad. I'm expecting teams of size 4, maybe slipping to 3 at some point in the first couple of weeks here, and that's a perfectly reasonable thing to have happen. We can't do any less than that. We can't have a ninth team. We can only have 8 teams. I have enough hardware for 8 teams. There are 8 specific different platforms that you can access, and that's all that we have there. And like some of your other class projects, as you submit things at the end of every one of these machine problem assignments, I am going to ask you to just give me an honest answer in terms of what was the relative workload breakdown. It doesn't need to be if there's 4 people on a team. Well, everyone did exactly 1/4, 1/4, 1/4, 1/4. That's unlikely anyway. You can say that if that's the truth. I really want to know about the 100% cases and or the 0% cases, um, just to make sure that everyone's kind of doing their part of this class. Just to go back to where this thing is, if you go to your Canvas and sort of the main CPRE 480 Spring 2021 Canvas, go to Schedule, and it's on the right-hand side under Team Formation Survey there, and that should open up a survey, and let me know if that's not the case. That's where I put it. It may also show up under assessments if you have, or quizzes separately. It's not a real quiz. It's not graded in any way. My requirement for everyone is to fill that out today. Ideally, right now. I've left some time here. Class has not, the time has not officially ended, but we can stop the recording in just a moment here. Fill that out today. Give an honest answer. Feel free to use Discord if you want to start planning who you'd like to have as a team. And if everyone agrees that that's the case and the skill set seems like a good match, I'd be happy to have you self-form teams as you go here this first week. But I do need to have all the teams set well in advance of tomorrow so that you can see the assignment, so that you can get started in reading the assignment even before tomorrow, and that we can start on Wednesday make sure all of our basic technology works collectively across the class, and then actually get started in earnest. So I think I'm actually going to end the recording right now, but I'd like people to stick around, and we can have a little bit of Q&A. We can also just discuss anything you'd like to talk about. And if you haven't done so yet, please do take the time starting now to fill out that survey. Otherwise, it's an experiment. We're going to do the best we can this semester. I'm really really excited about it. A little scared, a little frightened to be honest, but I think we're going to have a fun time, and we're definitely going to learn a lot this semester. That I can absolutely guarantee you. But otherwise, stick around, and for the rest of you, I'll see you tomorrow.